We will continue our discussion on decoding of LDPC codes. Today we are going to talk about probabilistic decoding algorithm. So, we are going to talk about belief propagation algorithm. So, before we do that, we are going to prove some results and then use those results for decoding of LDPC codes. So, we are going to use this lemma theorem to prove the decoding algorithm results. So, what is this result? Which says if you have a sequence of m independent random variables, which we denote by A. So, A1, A2, A3, Am are m independent random variables, and probability of Ak being 1 is given by P of k, then probability that A has even parity is given by this expression, and probability that A has odd parity is given by this expression. Now, we will derive our expression for decoding algorithm based on this result. So, let us first try to prove this result. So, let us consider a function of the form this 1 minus PL plus PLT. So, if we look at the coefficient of t here, this will give us the probability of t i's. Now, we can similarly consider this function where this plus has been replaced by minus here. So, this function is identical to this, except that the odd powers of t will have minus in expansion. So, if we expand this and we expand this, if we add both of them together, what we will get is all the odd powers of t will go away. Okay. So, what we will be left with is even powers of t which are doubled up, and odd powers have cancelled out. Now, if we put t equal to 1 and divide by 2, we will get essentially probability that A has even parity, because we are left with only powers of t which is even. And similarly, we can also prove probability that A has odd parity. Now, in this case, this will have all terms positive, odd powers also positive, this will have odd powers negative. So, if we subtract this from this, we will get basically the probability of odd parity, and that is basically given by this. Now, the same result can also be proved using mathematical induction. So, if you want to prove it using mathematical induction, let us just say we take m equal to 1. If we take m equal to 1, what do we get here? For m equal to 1, we get basically half plus half 1 minus 2p1. So, this is nothing but 1 minus p1. And what is p1? P1 is the probability it is 1. So, what is the probability it is even parity? It is 1 minus p1. So, this relation holds for m equal to 1. Now, let us see it holds for also some m. Then we have to show that it also holds for m plus 1. Now, if it holds for m, to show that it holds for m plus 1, we have to find what is the probability that sequence of m plus 1 independent random variables have even parity. Now, when will the m plus 1 independent random variables will have even parity? They will have even parity when m of them have even parity and the mth bit that we get, mth width is 0, or sum of m independent random variables, they give odd parity, and the mth bit that we receive is actually 1. So then we will get m plus 1 as even parity. So is it clear? So there are two cases, two ways in which we can get even parity when we are considering m plus 1 independent random variables. Either m of them had even parity and m plus 1 is actually 0, or m of them add up to odd parity and m plus 1 is also odd parity. Okay. So what is this probability of m being even? That's given by this. What's the probability that m plus 1 is 0? That is given by 1 minus p m plus 1. What is the probability that m of them is odd? That's given by this probability. And what's the probability that m plus 1 random variable is 1? That probability is given by p times m plus 1. So the overall probability will be this multiplied by this plus this multiplied by p m plus 1. And if you simplify this, we can show that this plus this will come out to be 1 plus 1 k equal to 1 m plus 1 1 minus 2 p k. So details of the calculation I am just leaving it, but this is how, using mathematical induction, we are going to prove that this also holds true for m plus 1, and hence proof. Similarly, we can prove that probability that A has odd parity is given by this expression. We will first show that for m equal to 1, this is nothing but p1, so that it holds true for m equal to 1. Assuming it holds for m, then we have to show it also holds for m plus 1. Now for m plus 1 to have odd parity, two ways: m has odd parity and the m plus 1 bit that we get is even parity, is 0, basically is 0, or m has even parity and m plus 1 bit that we get is actually 1. So similar to this case, we can also find out these probability, and if we add them up, we can show that this will be equal to half minus half product from k equal to 1 to m plus 1 of this. So we can say that probability that A has even parity is given by this, and probability that A has, so some of these m random variables have odd parity is given by this. So these are the crucial expressions that we will be using in our decoding algorithm. So let us consider an example. So this is our parity check matrix. We will first describe the notations that we are going to use, and then we will state the decoding algorithm and the corresponding equations, and then we will illustrate using one example. So we are using C to denote our code word. So this is an n bit code word, C0, C1, C2, Cn, that is our code word. Now this code word is modulated using BPSK modulation. So we are mapping 0 to 1, we are mapping to -1. So that is your BPSK modulated version of the code bits denoted by x of I. Y of I is your received modulated code word. So this is, we are considering an additive white Gaussian noise channel with noise variance given by n square, and it's a 0 mean Gaussian noise. We use this notation Rj to denote the location of ones in row j. Now, what does location of ones in the rows of the parity check matrix denote? It denotes the bits that are participating in the parity check equation. So, let us take this example. What is R0? R0, so what are, so R0 correspond to the 0th row, which is this row. Now, look at the bits that are 1 here, 1, 2, 3, these are the bits which are 1. So, R0 corresponds to, let us just label them 0, 1, 2, 3, 4, 5, 6. So, R0 corresponds to 0, 1 and 2. And what does it mean? It means for the first parity check equation, the bit number 0, 1 and 2 are participating. Similarly, R1 will be this. R1 will be 3, 4 and 5. R2 will be 0, 3 and 6. And R3 will be 1, 4 and 7. So, that is your Rj. Now, we use this notation Ci to denote the location of ones in column I. Now, what does location in column I denotes? It denotes that ith bit it participating in how many parity check equation, which parity check equation. So, let us look at what is C0. So, this was again 0, 1, 2, 3, 4, 5, 6, 7. So, C0 is what? C0 is, again this is, just call it 0, 1, 2 and 3. So, this is 0th parity check equation 1, 2 and 3. So, bit number, so if we look at column 0, so you can see this bit is participating in 0th parity check equation and second parity check equation. So, C0 will be 0 and 2. Similarly, C1 is going to be 0 because it is participating in 0th parity check equation and 3. Okay. You can take any, let us say C4. What is C4? Fourth bit is participating in parity check equation 1 and participating parity check equation 3. So, like that you can find out what is Ci. Fine. Now, we define this set Rj minus a particular element I. So, let us go back. So, what was our R, let us say R0, what is R0? R0 was location of ones in 0th row. So, that location was 0, 1 and 2, right. So, if I define let us say R0 slash 0, that would be then, because R0 is what? R0 is 0, 1, 2. So, R0 minus 0 will have 1 and 2. Similarly, R0 minus 1, this will be set containing 0 and 2, and this will be set containing 0 and 1. Similarly, we define this set Ci minus this element j. So, for example, in this case let us say C1 is 0, 0, 3. So, C1 has elements 0 and 3. So, if we define this, sorry, this notation is like this. This is this 0, this will be 3, or C1 will be 0. Okay. Now we define by Ckj the kth bit in the jth parity check equation involving code bit Ci, that is denoted by Ckji. So the received sequence corresponding to this transmitted sequence would be then, this is the modulated version and this is the noise added. So this is the received signal corresponding to this code bit. Now for an AWGN channel, we can compute this probability that Cib is 1 given a Yi. This can be given by this expression. And we denote by Pkj the probability that Ckj is 1 given a received sequence Ykj. So then we can write down the expression for a posteriori probability of our code bit Ci given our received sequences Y and given that the parity check constraints containing Ci has been satisfied. So what's the probability of Ci being 0 given a received sequence Y and given that the parity check constraint containing involving Ci has been satisfied? This is given by, divided by probability of Ci being 1 given Y and Si. This expression is given by this expression. And we are going to use the theorem that we have proved in the beginning of the lecture to derive this expression. Namely, if you have m independent random variables, what's the probability that some of them has even parity and some of them have odd parity. We are going to make use of that result to derive this expression. So let's see. So from base rule we can write this probability as probability of Ci being 0 given Yi multiplied by probability that the parity check constraints are satisfied given Ci is 0 and the received sequence is Y. And similarly, denominator we can write that's probability of Ci being 1 given received sequence Y and multiply by the probability that parity check constraints are involving Ci is satisfied when Ci is 1. So this probability is nothing but our Pi. If you go back, what was Pi? Pi is probability of Ci given Vi. So that's Pi. So then this upper term would be 1 minus Pi. Okay. Now let's pay close attention to these terms then. So what is this? Given that my code bit Ci is 0, when will parity check constraint involving Ci will be satisfied? It is when sum of other parity bits involved in the parity check constraints, they add up to have even parity, right? So this event Ci will be satisfied if each of these parity check equations where Ci is involved, other than this Ci bit, if all other bits involved in the parity check equation, in case of a regular LDPC code, that number is WR minus 1. If all those bits have even parity, because Ci is 0, so the other bits should have even parity, then only the parity check equation involving Ci will be satisfied. So we need to find the condition that sum of other parity check bits involved in the parity check equations where Ci is participating, they should have even parity. Now from the theorem that we have proved, we know What is that probability? Probability that other than Ci, WR minus bits, they have even parity. That probability is given by this expression. If you go back, probability that they have, probability that m random variables have even parity is half plus half product of 1 minus 2 pk. So, probability that WR minus 1 bit, so half plus half. Now, pay close attention to this. This is 1 minus 2 pk. Now, what are the bits that we are considering? Now, what will Rj tell us? Rj will tell us the jth parity check equation, and Rj minus I, where I is Ci bit is involved, and this is minus I. So, the other bits other than Ci which are participating in the parity check constraint, product of this, they should add up to have even parity. So, this is a set where Ci is participating in a parity check constraint. So, other than Ci, other bits have even parity. That is captured by this particular set. And this should hold for all parity check equations involving Ci. So, this should be hold for all WC parity check sets where this particular bit Ci is participating. So, that is why you, assuming that Yi's are independent, I can then write the probability as product over all such parity checks equations where this is involved. So, I can write down then probability that my parity check set constraint is satisfied given Ci is 0 is given by this expression. And I can follow the same logic to find out the probability when Ci is 1. When Ci is 1, what I want, the other bits should add up to have an odd parity, and that is given by this expression, and this should hold for all parity check, WC parity check equations. So, this is assuming independence, I can multiply by each of these probabilities. So, this is the probability of this parity check set, parity check constraint getting satisfied when Ci is 1, and this is the expression when Ci is 0. So, if I plug these values in my expression here, this expression, what I get is the expression for this. Okay. So, as we have said before, we are representing this LDPC code using the standard graph, and there are two types of information which are getting propagated. One is one set of messages which is from the message nodes going to the variable, going to the parity check nodes, and there is one set of message which from the parity check nodes coming back to the message nodes. So, we are denoting by RJI the message which is passed from jth parity check node to the ith bit. We are denoting this by RJI. So, what is RJI? RJI is the probability that jth check node is satisfied given x is plus 1. So, this is a probability that jth check node is satisfied given Ci is 0, and other bits are given by distribution given by this Q. Now, what is this Q distribution? We will come to, so there are two types of messages. As I said, there is one message. So, if I draw any Tanner graph, let us say, just draw any Tanner graph, let us say this some graph I am drawing. So, there is one set of messages which is going from message to this check nodes. Okay, this is one set of messages which are going like this, and this another set of messages which is coming from the check node to the message bits. So, we are denoting by QIs the message which is passed from bit node I to the jth check node, and we are denoting by RJI the message which is passed from the check node to the bit node. Now, probability of this being x being plus 1, which is basically correspond to Ci, the code bit being 0. This probability is defined as what is the probability that jth parity check constraint is satisfied given that Ci ith bit is 0 and other bits are given by distribution given by Qi. Now, what is the probability that jth parity check constraint will be satisfied given Ci will be 0? That probability is given by the condition that all other bits that are taking part in the parity check constraint other than Ci bit, they should have even parity, and that is given by this expression. Similarly, we can find out what is the probability that RGI is minus 1, this is 1 minus this probability. Now, what is this Qij? It is a message passed from the bit location I to the jth parity check node, and this is, so Qij being plus 1 is given by what is the probability that Xi is plus 1 given receive sequence Yi and information from parity check nodes other than the jth parity check node. So, what is happening is when you are decoding, because each bits are participating in multiple parity check equations, so you are getting some independent information from other parity check nodes, and that information you want to pass it to and spread it around in this network, and this probability is given by this expression. So, there are two types of messages, again I repeat, which are being propagated in this graph. One is a message from the message nodes to the check nodes, and then check nodes are sending some information saying okay, whether these parity check constraints are satisfied or not given input bit is 1 or 0, and they are passing that information. So, these information Qis are passed from message nodes to the check nodes, and these messages Ris have been passed from check nodes to the message node. So, then how does this whole process go? So, first step is we initialize the probabilities that we are going to send from the message nodes to the check node. So, we calculate this Pi and we calculate this Qis. These are messages we will send from the bit node to the parity check node. Okay. So, that is the first step, initialization step, that we are calculating the initial messages that the bit nodes will send to the check node, and that is basically based on channel likelihood values. It is given by this expression. Next is once these messages are sent to check nodes, then check nodes will do local computation and it will send this Ris back to the bit node. So, pass information from check nodes to the bit node. So, check nodes are going to pass these information Ris back to the bit nodes, and this is given by this expression. Now, once you get this updated Ris from various check nodes, then these Qis are updated. So, you are going to then send modified information, these Qis, to the parity check nodes, and this is basically given by this. You can do some normalization, these are Ki's are just some constant, you can do some normalization. And finally, we will compute the a posteriori probability, and that is given by this expression, and this we have derived earlier in the lecture. Okay. So, to repeat basically how this whole process is going, you have this receipt values from the channel. Based on that, you compute your initial Pi's and Qis. Now, this information are sent to check nodes. Now check nodes do local computation, that what's the probability that the check node will be satisfied given a particular bit Ci is 0 or 1, and then they pass that information to along the edges back to the bit nodes. Now these bit nodes are getting information from other check nodes as well, because each bit node is connected to multiple parity check equations. So it takes those input into account to update its QIs, and this process is continued in an iterative fashion until all the parity check constraints are satisfied. So finally, basically once you compute the a posteriori probability, then if Qi being minus 1 is more than 1, you decide in favor of 1, otherwise you decide in favor of 0. So let us take an example to illustrate the decoding algorithm. So we have a low density parity check matrix given by this. We have 8 coded bits. This is the Tanner graph corresponding to the parity check matrix. We can just quickly check it. So the first parity check equation involves these 3 bits, first 3 bits. So you can see the first parity check equation involves this, this and this. Second parity check involves 4th, 5th and 6th bit. That's second parity check involves 4th, 5th and 6th bit. This involves 1st, 4th, 7th, and that's 1st, 4th and 7th, and similarly we can verify for this also. Okay. So this is a Tanner graph corresponding to the parity check matrix that we have drawn. So these are the bits, 8 bits which were transmitted. Now after modulation, because we were mapping them as minus 1 Ci, so 1 is getting mapped to minus 1 and 0 is getting mapped to plus 1. So that's, these are the modulated bits, and noise variance was 0.5. So what we get is these are the received values. So these are my Yi's. Okay. Now what is the first step? I will take this Yi's and I will compute my Pi's and Qi's, initial Pi's. So I am going to first compute my initial Qi's, and that's basically given by this expression. So I am just stating this. So I compute this Qi's. Now again, just pay little attention to what Qi's are. Qi is the message passed from ith bit to the jth parity check constraint. So if you label your nodes from 0, 1, 2, 3, 4 and similarly label parity check constraints, so what you are going to notice is, so you need to compute your Qi's for in this example. So this is 0, 1, 2, 3, 4, 5, 6, 7. Similarly, this is 0, 1, 2, 3. So you will compute Q00. So Qij is the message passed from ith node to the jth check node, right? So Qij's you need to compute for in this particular example. So let's look at 0th node. So you need to compute Q00 because your message you are sending from 0th node to 0th parity check. You need to compute Q02 because you are sending message from 0th bit to the second this thing. You need to compute this Q10. You need to compute Q13, right? You need to compute Q20. And how are these initially computed? These are initially computed based on what are the received values Yi's that we have received. And that's precisely what I have shown here. So I have You can see here these are the computed values of QIs, and pay close attention to these indices. This denote that ith bit is sending information to the jth parity check constraint. Okay. So once we have computed this Qij, the next thing that we need to do is these parity check constraints are now going to check, okay, given that the bit is 0, what is the probability that parity check constraint is satisfied? Given the bit is 1, what is the probability that parity check constraint is satisfied? And those are given by these R's, Rij's, right? What is the probability that 0th parity check constraint is satisfied given the 0th bit is +1? Now, what is that probability? That probability is given by, so we are looking at first parity check constraint. Now, given that first bit Ci is 0, what we want is the other bits which are involved in the parity check constraints, they should have even parity. So, let us look at the H matrix for the first row. So, this is R0. R0 is 0, 1 and 2. So, given that this bit is 0, what we want to find out is what is the probability that sum of these two add up to even parity, and that is what we are doing here. Note here, ith belongs to R0 minus this 0th term. So, here you will have two terms, one is corresponding to I being 1 and other I being 2. Why? Because your R0 was 0, 1, 2. So, R0 minus this element 0 is nothing but 1 and 2. So, here in this product you will have two terms, one corresponding to Q10, other corresponding to Q20, because in that 0th parity check equation, other than the first bit, the bits that are participating is that, other than the 0th bit, other bits which are participating is bit number 1 and bit number 2. So, this is the probability that parity check constraint is satisfied given Ci is 0. And similarly, we can calculate the other Ri's. I am not going into detail of that, it is just the same procedure repeated. So, once we calculate this Qi's, Ri's and initial Qi's, then we are going to update our Qi's, and again we follow. So, we find the product over all those check equations other than that particular bit, and we repeat this for Qij being +1 and -1, and we can normalize these probabilities so that they sum up to 1. So, if we normalize it, these are the probabilities that we are getting, right. And next thing, finally, after we have computed one round of iteration, what is one round of iteration? You send these Qi's to check node, then check node gives you back Ri's, you update your Qi's, and once you do that, you can then find out the a posteriori probability, which we have done here. So, the probability of it being 1, probability of this being 0, and then based on, you can again you can normalize these probabilities. So, that comes out to be this. Now, based on whichever is more likely, you decide in favor of that. For example, in this case, Q being -1 is more likely. So, the bit which was transmitted was 1. Okay. So, to recap how this probabilistic decoding algorithm works, you have your receive sequence, you compute this probabilities Q's, message bits, send it to the check bits then do some local computation, send some information back. Now, this process goes on and on until basically all the parity check constraints are satisfied or the maximum number of iterations have reached. Now, this we have done for the first bit. You can do the same thing for other bits as well. In fact, the beauty of this algorithm is you can do this whole operation parallelly. So, one of the nicest feature of this algorithm is computation per bit per digit is independent of block size, and average number of iterations required basically to decode is typically bounded by log of n. After that, you started getting correlated information back. So, with this we will conclude our discussion on probabilistic decoding of LDPC codes. Thank you.